Okay, welcome to Module 15b. We're going to continue talking about ANOVA, in particular ANOVA in relation to the two-sample t-test that we learned way back in Chapter 12, and also some about the interpreting the output of a multiple ANOVA or a two-way ANOVA. So if you think back to what a two-sample t-test was trying to tell us, that was allowing us to test the null hypothesis that mu1 is equal to mu2. Sorry about that, mu1 equals mu2. When we said what's the null hypothesis that ANOVA allows us to test, well, that would be a generalization of that. Mu1 equals mu2. If there's three groups up to mu3, they're all equal means, or all the way up to some mu k value where that's the maximum number of groups. But what happens if k is equal to 2? What if there are just two groups? ANOVA and t-test seem like two very different tests. Which one is better? Which one should we trust in terms of doing the test? So we're going to work through an example like that. So imagine you've got something like plant height. So these are measurements of height. They should probably have centimeters on here. That's all these measurements in the table under two different conditions, low light and high light. So you're interested in whether the mean of plants grown in low light equals the mean of plants grown in high light. And obviously the sample means are going to differ, even if in fact the parameters are equal to each other just because of sampling error. And we've got small sample sizes here, 6 observations in each case, and we've got substantial variance, at least in the low light condition. Okay, so there's some data that we might be interested in testing this null. The alternative is just that the means do not equal each other, obviously. So how can we go about doing this? Well, we can calculate some more summary stats. In ANOVA, we use this big N, which is the sum of the sample sizes over all the groups. So in this case, it's 12. Just 6 plus 6 is 12. If we were thinking about a t-test, the numerator of the t-test is the difference in the sample mean. So that's 217 centimeters minus 917 centimeters, so 11 centimeters. So that's a measurement of how much the sample means differ. But obviously it's still possible that the population means are zero difference. So, all right, well, let's just think about calculating a t-statistic. Well, we have in a two-sample t-statistic, we need this pooled variance here. If we think about how we do an ANOVA, one of the first things we have to calculate, one thing that ends up in a denominator of ANOVA is this SS error, the sum of squared errors term. That's with this general formula here where we're weighting the variance from each group by 1 minus its sample size. So if we just had two groups, it's N1 minus 1 times the variance in group 1, and N2 minus 1 times the variance in group 2. Well, that's actually the numerator in the pooled variance. So we see a connection here already between ANOVA and a two-sample t-test. And what goes in the denominator of the pooled variance? Well, it's just the sum of those weights, N1 plus N2 minus 2. That's big N minus 2. So it turns out that pooled variance, even though we didn't use this notation of sum of squared errors, there's already one connection there. We did something very similar in ANOVA and a t-test. So we put in the numbers for this example. In both cases, the sample sizes were 6. So we have 5 when we do the subtraction for the weighting terms. And these are the variances that I had on the previous summary slide. So we get an SS error of 173.67. So that becomes the numerator of our pooled variance. And the denominator is 12 minus 2, so that's 10. So that gives us a pooled variance estimate of 17.4. Okay, so that's making some progress on both of the test statistics, on the T and the F stat. Okay, so we've done this. Here are the sample stats we had before. We just talked about how to do the pooled variance. Remember, the next part of the t-test was actually figuring out what the standard error for the difference of means was, and this was the formula for that. It was the pooled variance times this factor that has to do with the sample sizes, 1 on n sub 1 plus 1 on n sub 2. There, 1/6 plus 1/6, so that's 2/6 is what that adds up to, and 17.4 is what we got from the pooled variance there. So if you multiply those two together and take the square root, you get 2.406. And that's some measure of essentially how much slop there is in a difference in sample means when we have this much variation and these sample sizes. So that's our standard error for the difference in means. The t-statistic itself down here, so this is all recapping what was on the previous slide, the t-statistic is the difference in sample means minus the hypothesized difference in sample means if the null is true. We're testing the null hypothesis that the two population means are equal to each other, so this is just, this thing will go to 0, so we can drop that term. So this is our t-statistic, the difference in sample means over that standard error that we just calculated there. So 11 is our difference in sample means, and 2.46 is our standard error, so that's our fraction, and we end up getting a t-statistic of 4.57, which is a pretty substantially large t-statistic. Remember, we have to look in the t-table to figure out if that's a significant difference. This is summarizing all the stats that we calculated thus far on the previous slides. There's our t-stat. I went ahead and looked at the t-table. So the degrees of freedom for this two-sample t-test, remember, is n minus 2. We had slightly different notation back when we taught it to you originally. We taught it to you n sub 1 minus n sub 1 plus n sub 2 minus 2, but that's the same thing as capital N minus 2. So in this case, capital N is 12, so our degrees of freedom is 10. So that's why I looked at the 5% tail for a two-tailed test in the t-table, and I got this critical value of 2.23. Our observed test statistic is larger than that, so it's further off in the tails. Remember, the t-distribution looks a lot like a normal distribution, just has fatter tails. So 2.23, that denotes, sorry, that's terrible handwriting. That denotes the 5% tail, and it would also be negative 2.23, right? But our observed value is 4.57, even further out here. So we keep going down the table out. So even out to the 0.01 level, we have a critical value of 3.17. So our test statistic's even more extreme than that, which means our p-value is less than 0.01. So we can say that the p-value is less than 0.01. There seems to be a difference in these populations. We have enough samples to conclude that or reject the null hypothesis. And in this case, the low light seems to have higher growth for this particular plant. Okay, so hopefully that rings some bells and you remember that from chapter 12. Well, we had calculated this SS error here in the step towards calculating the pooled variance. Let's follow up on using the SS error and let's go ahead and calculate the ANOVA. So if we did, there's our SS error. The other thing we need to do for an ANOVA is calculate the grand mean. So that's a weighted average, N1 times the mean of group 1, N2 times the mean of group 2 divided by the total sample size. Gives you a 14.67. That's right in the middle of these two values because they have equal sample sizes. The weighted average is just the average. So there's our grand mean, 14.67. And if we have the grand mean, then we can calculate the sum of squares groups. So that's not something that's obviously connected to a two-sample t-test, but we can go ahead and calculate it. It's the sample size of the group times the deviation of the group from the grand mean, and we square that deviation. So this is putting in all the numbers. For the group 1, the mean was 20.17. The grand mean is 14.67. For group 2, 9.17, and we subtract the same grand mean. So the grand mean is being subtracted from both of them, and the different group means there. And then they're both upweighted by their sample sizes. So I get a sum of squared groups of 363. I'm going to start putting this in an ANOVA table here. So we have 363 for the groups sum of squares, 173 for the error sum of squares. Remember, the degrees of freedom for the groups is k minus 1. That's the degrees of freedom in the numerator. And the degrees of freedom in the denominator is n minus k. So in our case, it's 2 minus 1. That's 1 degree of freedom in the numerator, and 12 minus 2. That's 10 for the denominator degrees of freedom. So that's where those numbers are coming from. And then we're going to calculate the mean squared error by dividing 363 by 1 and the mean squared group by the fraction in the first row and the mean square error by the fraction in the second row. So 363 divided by 1 and 173 divided by 10. So those are our mean squares. Those are both estimates of the same variance if the null hypothesis is true. So we can calculate the F statistic by creating the ratio of those two. So in this case, the F statistic is 20.9 because the 363 is almost 21 times larger than 17.4. So that's a number that's pretty far from 1, and we can look up in the F table what the p-value for that is. So if I look up in the F table for 5 degrees, 0.05 alpha level, the degrees of freedom are 1 for the numerator and 10 for the denominator. I get a critical value of 4.97. That's quite a bit smaller than 17.4. So 17.4 is more extreme, right? So we have a smaller p-value than 0.05. We want to go ahead and look at the next table. If we look at the 1% level, alpha, we get the same degrees of freedom, 1 and 10. We get 10.04, and that's still more extreme than that. So once again, we say that the p-value is less than 0.01, which is the exact same conclusion that we had when we did the two-sample t-test. And here are the summaries of the test statistics that I calculated from the data, and the 5% critical values and the 1% critical values for the T and the F respectively. And I know this just looks like sort of a confusing barrage of numbers perhaps, but it turns out that if you were to square 4.57, you get 20.9. If you were to square 2.23, you get 4.97. If you were to square 3.17, you get 1.04. So it turns out that even though the mechanics of the test sort of feel different, we saw one connection between the pooled variance and the SS error, but apart from that, it seemed like we were doing a pretty different thing. They actually are capturing the exact same signal from the data. It's just if you were to square the t statistic that you get from a two-sample t-test for some degree of freedom, that's going to be equal to the F statistic for 1 degree in the numerator and that same degrees of freedom in the denominator. And you can go look at the tables and compare the column of the table that corresponds to 1 degree of freedom in the numerator, and you'll notice that all the critical values match up between this. If you square the T critical value, you'll get the F distribution. So this is just pointing out that there's multiple ways to generate a test statistic, but if you're capturing the signal in the data, you're going to get the exact same conclusions in terms of the p-value, and that's what we're relying on when we conduct the test. That's what we're trying to figure out, whether the p is less than 0.05. So you don't have to sweat which one is the correct test. You can do either test. They're going to give you the same answer. So why do we even teach the two-sample t-test? Well, the t-test is nice if you've got a situation where the null hypothesis is that these groups are not equal to each other, that maybe one's off by 5 or something. It's a more sort of general form, and then you would substitute in 5 here, and you could do a different null hypothesis. The T statistic is also really useful because remember, as we've discussed numerous times in the class, the T is the difference that you're observing, but in the sample, expressed in terms of how many standard errors away from the expectations it is. So that's kind of a handy thing. So the test statistic itself is more meaningful to people. And ANOVA can be nice to do. I didn't do it in this case, but remember, if we were to fill out the SS total here, if we were to add up those numbers, we could calculate an R squared in ANOVA, and that gives us that nice summary of the percent of variation explained by the grouping. So, there's these kind of, secondary reasons you might prefer to do a t-test or an ANOVA in the example, but since they're both testing the hypothesis that that each of the samples is drawn from a normal distribution with a mean of mu and a standard deviation of some same sigma, that's true of the Y1 and Y2 under both. That's the null hypothesis that's being tested. That both of the samples are drawn from some normal distribution with the same mean and the same standard deviation. Because it's the same null that we're testing, it's the same information that we're using in each of these tests, we get compatible results. So I'll post a little discussion of mathematically why this is the case at some point on Blackboard. You're not going to be quizzed on that, but if you're curious about a derivation, then you can actually prove that these test statistics are always going to be, one's going to be the square of the other. So note that connection, and hopefully that helps make sense of why all these ANOVA steps, which seem pretty disconnected from the data, are actually capturing the core information that we relied on in the much simpler two-sample t-test and generalizing that to a larger number of groups. Okay, so we're not going to go into depth in the other tests in Chapter 15. I just want to talk a little bit about two-way ANOVA. A two-way ANOVA is when you're looking at two categorical explanatory variables and you have one numerical response variable. And it's worth mentioning because we've talked about factorial experimental designs, and so we often use something like a two-way ANOVA to analyze a factorial design if we had two factors. So, for example, think maybe rice is harvested twice a year. So you've got a spring harvest and a fall harvest. And you're also interested in trying a new fertilizer. So you measure output, the kilograms of rice harvested. And that's, you want to say, is that independent of which harvest, the first or the second, and which fertilizer, present or absent? So presence or absence of fertilizer is one explanatory variable. First or second harvest is the second explanatory variable. And the response variable is the kilograms of rice harvested. And so that's the situation that we talked about here. And you can, it turns out you can do two-way ANOVA, which is a nice hypothesis test for the reasons that we emphasized that a factorial design was nice, because it allows you to look at multiple things. You can, in a two-way ANOVA, you can test three null hypotheses. The first one is just the first categorical variable has no effect. Categorical variable A has no effect would be the null hypothesis. So we call that a main effect of one of the categorical variables. The second null you can test is the categorical variable B has no effect, so no main effect for B. And then the third hypothesis is that there is no interaction between A and B. And so this interaction hypothesis you can get at when you do a factorial design, and you can pull out of it and two-way ANOVA. As I mentioned, we're not going to do the details of how you calculate the test statistics, but it turns out that there are just three different F statistics that you calculate from the data here. And it gets a little tedious to do this by hand. It's basically no one does it by hand. So we're not going to focus on the details in this course, but I do want you to be able to interpret the results of an interaction plot that is often used to summarize a two-way ANOVA. So it's useful to just think about what kind of results you could get out of this. So for instance, in that rice example that I mentioned, the first hypothesis you could test was that the first and second harvests have the same expected yield. The second hypothesis is that the fertilized versus unfertilized plots have the same yield. So those are the two main effects, the harvest, first versus second, and fertilizer, yes versus no. And then the third hypothesis, the interaction one, is any effect of the fertilizer is the same for the first and for the second harvest of the year. So there's kind of an additivity. So maybe one of these nulls is not correct and there's something going on, but the effect doesn't vary according to the combinations of categories. So hopefully this will make a little more sense as we go through the examples here. And these are interpreting these examples of the types of things we would expect you to do for a two-way ANOVA on a test. So here's the case where there's no effect of harvest and no effect of fertilizer. It may be a little hard to read these slides. Hopefully that zoom in will help. So there's two ways to explain to plot this data that are commonly done. So you have the response variable on the y-axis, and you say, well, I've got four combinations. I've got harvest, first versus second. I could put that on the x-axis, in which case I'd have to use the line codings, dashes versus solid line for no fertilizer is dashed and fertilizer is a solid line, right? And so that would be the plot. Here's an example where there's the do not reject the hypothesis 1, do not reject hypothesis 2, and there doesn't seem to be an interaction. It looks like all of the data are really similar, very close to 45. So all the points are sort of on top of each other. So we do not reject for hypothesis 1, hypothesis 2, or the interaction effect. Now you might ask, why did you put fertilizer in the line codings and harvest on the x-axis? Why didn't you put fertilizer on the x-axis? Well, you totally can. It's completely arbitrary. You want to put the explanatory variables on the x-axis, but we have two explanatory variables. So here's an example of the same data where we put no versus yes for the fertilizer, and first and second harvest are coded by different lines. It's hard to tell that they're different lines because they're right on top of each other in this figure, but that's what's going on here. So there's an example of an uninteresting two-way ANOVA where you fail to reject any of the null hypotheses. Here's an example where you have one main effect. So here, let's think about which main effect is present. If you are looking at the first harvest, fertilizer or no fertilizer, you're way up here around 55 for both of them. So there doesn't seem to be much of a fertilizer effect. Those lines are falling right on top of each other. But if you look at the second harvest, the points are also almost on top of each other. All right. But there was a big difference between the first and second harvest. So maybe you get better crop in the spring than in the fall, right? So that would be the first main effect you reject, and then you do not reject for the fertilizer test. They're basically right on top of each other, those points. And there doesn't seem to be any interaction. And the reason I say that is because, there's no kind of, you're seeing no effect of the fertilizer here and no effect of the fertilizer there. So you do not reject an interaction effect. And it turns out what we're looking for in an interaction effect is these lines being parallel to each other. So they're right on top of each other and they're parallel the entire way, so there's no evidence of an interaction. If we had chosen to plot the data in a different way, where we put fertilizer on the x-axis, now we can see that the second harvest is lower, but it's consistently lower whether or not you're fertilizing, and the first harvest is higher consistently. So you have, once again, parallel lines, so that would give you the same conclusion. We're going to reject the null hypothesis that the first and second harvests are different because we have that gap between them, but we do not reject the null that the fertilizer has an effect because these lines basically look horizontal. So there's no fertilizer effect. Do not reject. And do not reject interaction because we have parallel lines. So this is just pointing out that you can make these plots either way and you'll get the same conclusions. If you're asking how do I know whether or not we're getting significance, how do I know reject, you'd have to do full stats to know whether this is actually a significant difference. But when we ask you to interpret an interaction plot on the exam, we're just looking for, does it sort of look like, if we have pretty small error bars on here, does it look like there's an effect? We're not trying to trick you again. We just want you to, we're going to give you an example and say, okay, all of the effects that seem to be present, let's say there's statistically significance, what would the plot look like and how do you connect that to the conclusions you would make? Okay, so what if there was a fertilizer effect but no harvest effect? It's this very similar as the last one. So now we have one main effect. There's a big difference between no fertilizer and fertilizer, but there's not much difference between the first and second harvest. These are horizontal lines here, and since the lines are parallel on the plots, we don't see an interaction effect. Okay, well, what if we have both main effects? Both main effects are present, so we would reject the first null hypothesis and reject the second null hypothesis. So there seems to be a harvest effect, first and second. The second harvest seem to be lower in both of these cases, and there seems to be a fertilizer effect. Fertilizer is higher in this made-up example than the other one, right? So you see there's a fertilizer effect, and you see this drop here, sort of the average. There's your average for the second harvest, and there's your average for the first harvest. That is the first harvest to second harvest effect. So there's both effects going on. But once again, the lines look parallel, so it doesn't seem like there's any kind of interaction. We do not reject the hypothesis that fertilizer and first versus second harvest are acting additively or independently of each other. So they both have an effect, but their effect doesn't have any kind of interaction at all. It's just the sum of the effects that you would get. In fact, the way I sort of made up the data here is from 45 up to 50. That's your effect of the first harvest. You get 5 more kilograms in the first harvest, and then there's an effect of I think I made it like 7 or something for the fertilizer, and so but you can add 7 to either of these and get up to that point. So going from there to there, you have both the effect of the first harvest and the effect of the fertilizer, but they're just additive. There's no kind of weird interaction. So what does a weird interaction look like? This would be a case where we have all rejections of the 3 hypotheses that a 2A ANOVA allows you to test. Looks like there's a fertilizer effect, right? So the no fertilizer versus fertilizer, there's a difference between those. So that looks like an effect there of fertilizer. Looks like there's a harvest effect because the midpoint of those 2 harvests is not the same as the midpoint of the second harvest, right? So there's our harvest effect. But there also looks to be an interaction effect in that there's a very little distance here, but there's a bigger distance over in this side. And so the fact that the lines are not parallel means that, okay, in this case, what it means is you have higher yields in the second harvest, and the fertilizer is having a very large effect in the second harvest. It's having a small effect in the first harvest. So the size of the effect is not the same across the treatments. You could plot the variables in the other way, and you'd still see lines that are not parallel. Okay, so hopefully that makes sense. You can even have, at least in theory, you don't tend to see this happen very often in the real world, but you can have cases where you don't find a main effect, so you do not reject for either of the main effects. So the fertilizer, the average point between the two fertilized, the average point for the no fertilized or the fertilized, they both average out to right around 50. And also the average point for the first and second harvest also averages to right around 50. And so there's no sort of net effect of first versus second effect, but there is an effect of interactions because we can see there's big differences here. It's just they seem to cancel each other out so that as you go to the second harvest, if you're fertilizing, then you can get the same yield as you got from the no fertilization case in the first harvest. So anyway, this is kind of a weird case that doesn't show up, and it's much more common to see a case like this where you have main effects and you also have an interaction effects. But at least it is theoretically possible that you don't have main effects, but you can tell that there's some kind of interaction between the variables. So hopefully you can get a sense of the kind of questions you can answer with the two-way ANOVA and how you would interpret the results. We had some graphs looking like this a couple weeks ago when we were talking about experimental design because we were talking about factorial analysis and the ability to pick up on these interactions. And the two-way ANOVA is the way we actually do that in practice and put some stats behind it as opposed to just the figures. But since the analysis is very math heavy and tedious to do on paper, we're just going to make sure that you can interpret the figures for this one. You would use R or some other statistical software if you actually wanted to perform one of these tests. Okay.